Well, welcome to this session this morning. Thank you for those of you who have joined us live today, and also thank you for those who later on log in and download and view this. Welcome to this important session on the resilience and the important role in building resilience for groundwater, and in particular the issues around groundwater quality, some of the challenges, but also some of the opportunities and solutions that we have. I'd like to remind you that this is an interactive session, so please put in your questions into the chat box and comments. We'd love to hear from you during the session. And lastly, I'd like to introduce our moderator for this session, Nino Kukurik from IGRAC. A big welcome to him, and I'm going to hand over to him now for introducing the talks and the subsequent panel. Thank you very much.
Thank you, Dan, and good morning, good day, good evening, where you are. It's my privilege to welcome you to this very rich and promising session on groundwater quality. While almost half of the world population drinks groundwater every day, we still keep polluting this vital natural resource. And this is certainly not a legacy we should leave to the future. This session is a part of our joint effort to raise awareness about groundwater quality, and I'm sure it will be a very informative and interesting session. So, well, I suggest that we start. Dan, thank you.
What is groundwater, and why is it vulnerable? Most groundwater originates from precipitation that infiltrates into the underground, where it is stored in geologic formations called aquifers. Aquifers come in all sizes, from a few square kilometers to crossing borders of countries. Only a finite amount of groundwater can be stored in an aquifer. Globally, around 2.5 billion people rely on water supplied from underground aquifers as their main source of fresh water. Groundwater is also used for farming, especially during times of drought. Industry uses groundwater when surface water, like rivers, are not readily available or too polluted for production. Groundwater is typically extracted from an aquifer via shallow dug wells or deeper boreholes. Powerful electrical pumps can pump thousands of liters per minute from a single well. When groundwater is pumped faster than it is replenished by precipitation, the water level in a well declines. Groundwater stored in aquifers can be contaminated from the surface. Pollutants dissolved in surface water or precipitation can infiltrate and reach the groundwater. Pollutants released near a well are drawn to it and eventually get pumped to the surface. Therefore, the area around a well must be protected from pollution. Groundwater can be found very close to the surface or at great depth. A shallow groundwater reservoir is much more vulnerable than groundwater protected by thick layers of sediment or rock. Some pollutants occur laterally, such as fluoride, arsenic, or elevated salt concentrations derived from the surrounding rock mass. Groundwater contaminants can be both biological or chemical in origin. Human activities have polluted groundwater with excrement that contains disease-causing bacteria. Agricultural contaminants include pesticides or excess fertilizer, and examples of industrial pollutants are gasoline, solvents, heavy metals, and pharmaceuticals. Many of the most toxic pollutants are man-made. Once these pollutants enter the groundwater, they require a long time and much money to remove. Many water contaminants can neither be tasted nor seen. Chemical methods are required to test for this water pollution. An estimated 1.8 billion people are using a source of drinking water that is contaminated by fecal matter or bacteria. Access to safe drinking water is one of the most challenging problems of the 21st century. The potential of groundwater pollution increases with the number of people living close together. That is, an aquifer underlying urban areas with a high population density and industry is more likely to be polluted compared to groundwater reservoirs in more rural areas. However, in rural areas, wastewater is often not treated and therefore can contaminate the local groundwater with bacteria and agricultural pollutants. Populations that live near the coast often pump more water than is replenished naturally. This can lead to the intrusion of salt water into coastal aquifers. Once salt water pollutes an aquifer, the well must be shut down. Every person has it in their control to protect local groundwater from pollution at the community level by educating oneself about groundwater issues. A couple small examples include providing access to plumbed toilets rather than outdoor latrines, disposing toxic household products appropriately, and avoid using toxic products or packaging whenever possible. Farmers should only apply the minimum amounts of fertilizers and pesticides needed. Industry should follow less toxic or non-toxic alternatives in their production process. When building a new home, install an on-site wastewater treatment system to clean domestic water before it seeps back into the ground, and talk to your neighbors and friends about protecting their wells as well. Become involved in your community. Put pressure on local industries and regulators supervising them, and demand that environmental laws are being followed. This is what we can do to protect our groundwater and the groundwater for the future generations to come.
Great. Well, thanks, Gerard, for that excellent video. We hope that was a good introduction to the topic for folks and sort of a bit of a warm up, as it's particularly early in the morning for some of us. We're just going to move on now to a quick poll to get people thinking about the topic a little bit and engaging with it. And we're gonna start with one particular question that we'd like you to respond to around what you feel is globally what you feel is probably the most important groundwater quality challenge. And during the subsequent parts of the session, you can engage with that poll at any time, as far as I'm aware. So we're going to start that now. There are a number of different contaminant challenges, but we'd like to sort of decide what you feel is the most important one, and we'll get a feel from those involved in the session which one people feel is the most important and why, and perhaps some comments on to that effect as well in the chat box. So that's something to think about as we continue on with the next session, the next part of this session. So I'll hand over to Mahmoud for the poll.
Yes, sure. Thanks, Dan. Like I'm seeing people started, like our attendees started to answer the polls, and yes, we can see from the first poll, 32% answering pesticides for the first question, and then 27 for nitrates, 14 for salinity and arsenic, and as well as microbial contamination. And then in our second question, we can see that 33% they are answering better monitoring of groundwater, while 22% for reducing anthropogenic contamination sources, as well as more direct action to locally minimize. And then and 10% or 9% for better treatment of contaminated water.
Interesting. I was looking into this a little bit yesterday, and apparently agricultural pollution from nitrate is globally the biggest problem if we look at it globally. But of course, all these issues are important locally, and in some ways, looking at the issue globally is not always that helpful. But clearly, it's a big issue and a widespread issue. Right. Is it time now to move on to the case studies? So our next part of the session is 4 case studies, and it's my pleasure to introduce to you our first case study from Kallis Tindamugaya, who is based at the Ministry of Water Resources in Uganda and is the Commissioner for Water Resources and Planning and Regulation. The floor is yours, Kallis.
Good morning, everybody. My name is Kallis Tindamugaya from Uganda. I will be presenting a case study on how groundwater quality constrains groundwater development in Uganda. This is based on the work we have done through the groundwater mapping program. Next. We have quite a lot of groundwater development going on in the country since the 1930s. And we have a number of options for groundwater development. We have deep bore wells that are drilled beyond 60 meters. We have shallow wells, which are drilled by machine. Then we also have the wells that are drilled by hand, and also we have springs. Those shallow wells and springs have a challenge of water quality due to human activities, while deep boreholes suffer from quality related to the geological formation. Next. Groundwater development has been going on in the country for some time now. Next. And this development has resulted in 50,000 deep boreholes currently in the country, about 25,000 springs, and around 18,000 shallow wells. On average, per year, we drill about 1,000 deep boreholes and close to 1,000 shallow wells. And groundwater development is done for rural and urban water supply, and it is on the increase because groundwater is found to be easy to operate when systems are based on it. Next. Currently, water supply coverage is about 71% in rural areas and 79% in urban areas. And we are trying to achieve safe water supply to everybody by the year 2030. And we expect to drill an additional 40,000 boreholes and 30,000 shallow wells. And we're also planning to establish over 650 piped water supply schemes in smaller towns, and all of these will be based on groundwater. Next. We, however, have concerns with groundwater development in the country. Although a lot of money has been put into groundwater development, we have had challenges with the increase in water supply coverage because of a number of reasons. One is that we are constructing wells in areas with low groundwater potential, resulting in high failure rates. In terms of water quality, we're having water sources being constructed in areas with poor water quality, leading to either abandonment of the sources or limited uses, but also we spend money on expensive water supply options, and also found that we don't have tools to guide the development. Next. As a result of this work, we embarked on groundwater mapping program in 2001, and this program has been ongoing. And the objective is to assess and map groundwater resources in the country in terms of content and quality, and present this information on maps to guide the development and planning. Next. As a result of this, a number of maps have been prepared, but of special interest for this session are hydrochemical characteristic maps, which show data for various chemical parameters where we identify anomalous values. And those areas where we have anomalous values are avoided for groundwater development. We also have groundwater quality maps, which present different hydrochemical characteristics. And these maps show areas of potable water, areas of water of acceptable quality, and areas where groundwater quality is above maximum acceptable values. And these are based on the standards in the country. Next. We have, of course, also maps showing groundwater potential. And when we identify groundwater potential, we combine quantity and quality. So where hydrogeological characteristic maps show high groundwater potential in terms of quantity, if the quality is not good, then we declare those areas as having low groundwater potential, and those areas are avoided for groundwater development. Next. Next. So what I see here are maps. So such maps, what you see, for example, in deep brown, those are areas which show that groundwater quality is above maximum acceptable values. Areas which are light white, those are areas where the quality is good. Next. And when you see the map on quality, again, those areas with the deep brown, those are areas where the quality is not good. And those are areas, if you drill groundwater sources, then the sources will actually not be used by the people, they will be abandoned. So we are trying to avoid those areas because traditionally those areas have had boreholes drilled there and the boreholes have been abandoned. Next. So what have been the benefits of this program? Areas where we have prepared groundwater quality maps, we have had increase in drilling success rates because we avoid areas where the quality is poor. We have had reduction in failure of wells due to quality. We have also had reduction in cost of water supply systems, and we have also had increase in water supply coverage and more benefit to the people. And also the number of increased sustainable water sources has increased, and we have had faster achievement of water supply targets and sustainable development goals. Thank you very much.
Great. So thank you very much, Khalees. That's a really interesting overview of the situation in Uganda. We'd like to move on to our next case study now, which is from Claudia Ruz-Vargas, who's based at IGRAC, and it's going to be sharing with you some issues around water quality in South America and elsewhere. Thank you very much.
There are several challenges to produce an assessment of groundwater quality on a global scale. In this video, we are going to take a look at the most important methodological ones, but also at some opportunities to use new approaches. Priority contaminants in general include salinity, acidity, minor ions, nitrate, microbiological pollutants, contaminants of emerging concern, and geogenic parameters such as arsenic, iron, manganese, fluoride, and radionuclides. However, a major question is, what groundwater quality parameters can be brought into a global water quality assessment while bearing in mind that most groundwater quality issues are local? Whatever parameters are monitored, it is essential to ensure that the data are as accurate and reliable as possible. Often, laboratories performing the chemical analysis are accredited and have established quality procedures. However, the field sampling and analysis rarely has this level of quality assurance. Many pollution sources are localized, in addition to the significant natural variations in geology and hydrogeology across the aquifer systems of the planet. This means that pollution impacts on wells are often site-specific, making regional upscaling of results difficult. Local studies will need to be upscaled to regional assessments, but how should this be done? Machine learning has been used with good results, at a large scale and for geogenic contaminants, such as fluoride. These types of approaches still require more research before they can be applied at a global scale for contaminants introduced or at least mobilized by human activities, including salinity, chloride, microbes, nitrates, and more. One major complexity of assessing groundwater quality arises from the 3D nature of flow systems. Groundwater systems are often highly heterogeneous, meaning that samples from wells in close proximity may produce very different results, especially if they are taken from different depths. It is therefore necessary to monitor groundwater quality at different depths, using special borehole designs, such as cluster piezometer nests, or using multi-level devices. Other complexities are the long transport times involved in many groundwater flow systems. Groundwater pollution and rehabilitation may take place over considerably longer timescales than a surface water contamination problem. For example, nitrate currently stored in the unsaturated zone may result in contamination of the underlying aquifers for many decades. As well as long-term issues, groundwater quality may vary seasonally or respond to local short-term rainfall. Microbiological contamination of wells, for example, is often closely related to individual rainfall events. Hence, monitoring programs should be designed to collect groundwater quality data at the required frequency to show the temporal changes. For river systems, sampling downstream along the river gives an integrated picture of the water quality pressures from the catchment, but this is not the case with groundwater systems. Often, boreholes designed for monitoring water levels are subsequently adopted for measuring water quality, even though their location and construction may be unsuitable or suboptimal for this purpose. The construction materials, sample collection, and handling procedures must be chosen to avoid reporting false positives and false negatives. Field personnel need to be trained to a high level to ensure that they can obtain representative Remote sensing Earth observations, which are widely used to assess surface water quality, also have groundwater applications. Although Earth-observing satellites do not provide direct measurements of groundwater quality, recent research shows that they can produce proxies related to groundwater contamination processes and thereby provide indirect insights. One study showed that Earth observations about population density, road density, precipitation, temperature, and land cover in Uganda and Bangladesh were strongly correlated with microbial contamination levels in shallow groundwater. More generally, Earth observations can support predictive modeling efforts, as they can provide additional variables to include in predictive models. For example, predictions of nitrate and herbicide concentrations in groundwater rely on information about anthropogenic activities, such as land cover and population density, which can be derived from Earth observations. For more information, please visit www.groundwater-quality.org and read our perspective paper.
Great. So our next talk is from Isufu-Ouedraogo from Burkina Faso. He's based at the University of Fada and Gourma, and he is going to share with us
My name is Isufu-Ouedraogo.
issues of nitrate in Burkina Faso.
I'm assistant professor in groundwater ecology at University of Fada Gourma. My research area concerns groundwater quality at large scale, particularly in African context. I am also interested of use of machine learning such as random forest to access groundwater pollution. The title of my presentation is groundwater quality management in African scale with my colleague Bani van Tuster. Special thanks to UNESCO for invitation to attend this meeting of water. Groundwater research in Africa. 75% of African population depend on groundwater for basic water supply. Groundwater is used in irrigation, urban area, industrial development, and so on. Groundwater demand will increase in the future due to population increase, climate change, and we need groundwater to combat growing food security. Groundwater in Africa is under pressure. This is illustration with groundwater pressure in Africa. So the objective of the study is to improve our knowledge on the state of groundwater quality at African scale, supporting the monitoring of implementation of SDG in Africa. The specific objective of this work is to map first groundwater vulnerability for pollution at African scale, focus of nitrate groundwater vulnerability, and secondly to develop a statistic model that predict nitrate concentration groundwater in African scale, and third to access the time dynamic behavior of groundwater pollution at African scale. We use drastic methodology to map groundwater pollution in Africa. So drastic use 7 parameters, and we use also land use map, and we work at 15 spatial resolution domain. This map is our first output, shows that the groundwater pollution to map. Red color show very high vulnerability, and a yellow show very low vulnerability map in Africa. And secondly, we develop statistic model to predict nitrate concentration in Africa. So we use different physical attributes such as slope, depth, soil, land use, population density, population, and we use 2 statistic models, multilinear regression, random forest, and we use 2 types of nitrate simulation and nitrate observation through for meta-analysis. So the result of meta-analysis is illustrated to this map. The map shows the spatial distribution of data collected through the meta-analysis. A second map illustrating the different points of nitrate collected during the meta-analysis. The statistic output, the step shows statistic analysis of nitrate collected in the literature. We show that the mean value of nitrate in groundwater exceed the World Health Organization value. We have 55 milligram by liter in groundwater and African. This is African scale value. The 2 figures show the statistic model. The first is the multilinear regression, and the second is the random forest regression. We observe that random forest regression yield better to compare to multilinear regression. Another important result of random forest is to classify the importance of different attributes. So we observe that population density is the best strong variable explain nitrate pollution in groundwater. Also, the first important result is the groundwater pollution and the time dynamic. We observe that when you analyze the 2 years, the 2 years of groundwater, we observe that the groundwater pollution risk in Africa will increase during 1980 to 2010. We observe essentially the different increase of different percentage of 3 period. In conclusion, you can say that shallow groundwater in Africa is under pressure, and also population density explain the groundwater contamination in Africa, and the random forest is an opportunity to develop a very tool to develop groundwater pollution map at African scale. For the challenge of groundwater, it's important to integrate science, knowledge, and capacity building for challenge of groundwater quality in African scale. It's important to integrate the monitoring groundwater in African scale. This map illustrates the 2 country groundwater monitoring scale, South Africa and Burkina Faso. It's important to integrate political will and capacity building and knowledge dissemination at African scale. For more information, we can read this different publication. For future work, we would like to explore groundwater quality assessment in Volta Basin in West Africa, and it's important to collaborate with AQUIFER in Africa for the groundwater program focus quality, and it's important to maintain monitoring groundwater data in Africa scale. Thank you very much.
Great. For our next talk, we're going to move to South Africa, and this is being presented by Cornelius Ryman from Mvutu.
Good morning. I will provide feedback on the Cape Town aquifer use case. This use case comprised 3 different aquifers, but I will focus this presentation on the Cape Flats aquifer, which is a primary shallow aquifer that underlies the big part of the city and is prone to pollution from agriculture, industries, and informal settlements. The aquifer is used for irrigation and currently developed by the city for bulk water supply. We undertook a multi-layered stakeholder engagement process within the city's groundwater development project and with other stakeholders and communities. This project is an intrinsic part of the city's water strategy to become a water-sensitive city by 2040. The water quality assessment followed the same approach as for the other studies, using the metric triangle of in situ data, remote sensing data, and modeling data. However, we had to modify the approach to cater for specific aspects of groundwater, especially regarding the use of remote sensing. Based on the assessment, some products and services were developed, which I will describe in a minute. Water quality hotspots were identified based on in situ measurements and then extrapolated using remote sense data and modeling. The parameters of concern are salinity, nutrients, metals, and organic compounds due to agriculture, industrial areas, and leakage from sewage and stormwater systems as potential sources. Taking these hotspots and further identified areas of potential contamination, an aquifer protection scheme was proposed and developed, which comprised capture zones and groundwater protection zones, which are based on travel time between contamination sources and the production boreholes, vulnerability mapping to identify which areas are highly vulnerable to surface pollution and identification of potentially contaminating areas and the risk assessment of these sources, which can then lead, in specific cases, to rehabilitation plans. The second product was developed, and that is a water stewardship program comprising transformative arts practice and community engagement for awareness raising and transformation of living spaces, which will lead to reduction of surface pollution. The example at the bottom is the Lotus Canal, one of the identified potential sources of contamination, which runs through informal and formal residential areas, industrial areas, past the agricultural area, and discharges into Ramsar site before flowing into the sea. There are lessons to be learned from this use case and follow-up suggested to ensure the interventions are sustainable in the long term. Firstly, the success of this use case relied on the integration of the magic triangle, the wide stakeholder engagement process, and the availability of recent in situ data from the current investigation by the City of Cape Town. Moving forward, we suggest expanding the scope by including the surface and stormwater system and additional parameters to verify sources and pathways and to provide further solutions. Secondly, the water stewardship program should be expanded to other areas and communities within the Lotus Canal catchments. And thirdly, the approach should be rolled out or tested in other urban centers across Africa. Thank you.
Great. So we're now moving on from our case studies to our expert panel. We have a wonderful group of expert panelists for you today. To provide some reflections, some of their own unique reflections, and also to answer some of your queries and questions and stimulate the discussion on this topic. So I'm going to hand over to Inoka Kurik again, who will be the moderator for this part of the session.
Thank you, Dan, and good morning to everyone again. Good afternoon, evening, and this is live. This is not pre-recorded, so we have listened to very interesting presentations there. And if you have some questions, there's this chat and Cornelius and Calista with us, so maybe they can also immediately react. And we are going to move indeed to some discussion in a panel. And we have 4 panelists today. Really good one with a lot of experience on groundwater. We have Joel and Jane Hartwig and Toye, and I will start with Joel Podgorski, who is a senior scientist at EWAG. Joel, are you around? Yes, I see.
Yes, yep.
Yeah, very good. Good morning.
Morning.
Well, I know that you work on, among the other things, on a global assessment of arsenic and using sophisticated models, and you certainly need reliable input in terms of data. And so could you share with us some of your thoughts and experience with data collection, with the monitoring and use of data in your work?
Sure, thanks. So right, as you said, I'm working on these global models and regional ones as well, and it's often the case where, well, it's always the case that the more data that you can add to the model, the better. But it needs to be good quality data. And so in the past, we've used some of our own data, but you really can't as on a global scale collect enough data for what you need on your own, and so you rely on external sources. And it's key, of course, that these data are made publicly available. And from my experience, this is there are a lot of large data sources out there, but it can be a big challenge too. It often varies by country, depending on the policies of the country. I mean, in particular, I'm thinking of national groundwater monitoring programs, and these are expensive to run. And there is a natural tendency in some places to keep those data to themselves and to not share them, and because it's a big investment and it should be used internally is the general idea. The other perspective on this it seems to be going more in this way, thankfully, is to make these data publicly available. So not only can obviously the local researchers in country take advantage of this, but people all around the world are able to use this. And I mean, from the perspective of the country that's collecting these data, these external parties, groups can create new derived data products for free. And so, it's a benefit to the country that's actually sharing these data. And from my experience, this has been the greatest source of monitoring data from these large national surveys. Obviously, you can pick up data from individual publications, but usually there's maybe magnitudes, orders of magnitude less, lower quantity of data. But the quality of data can be quite variable, and it's important when making data available. It's nice to have as much information about how the measurements were made as well. Any uncertainties, but it's not always. This isn't consistently available because there's generally no standard. And if for sharing data, and if it is shared, then usually you're grateful and happy to get whatever is out there.
Many thanks, Joel, and sounds very familiar. Groundwater data and accessibility, availability, especially making this data public. Somehow they're still by many seen as a strategic sometimes, and quality of data is one of the challenges which I am going anyway to stress at the end of the session. But thank you for emphasizing this because it's a really one of the major challenges. Many thanks. Then I would like to move to a second panelist, which is Jane Daltrich, and Jane is Secretary General of International Association of Hydrogeologists. Jane, are you around?
Yes, I'm. Good morning, everybody.
Good morning. Good morning. I would just, I was thinking, in every language, you have some sort of saying, prevention is better than cure. And with your experience in both, but certainly prevention, could you elaborate a bit why is prevention of groundwater pollution so important and how we should improve the prevention, please?
Thank you. Yes, it's a cliche that prevention is better than cure, but it applies very strongly to groundwater protection as well as to the current coronavirus pandemic. Groundwater, as we've already heard, is vulnerable to contamination from agriculture, industry, urbanization, And one I'd like to stress is waste, both solid waste and sewage. But the impacts are very slow to be noticed. It's vital to put in place policies to protect groundwater and groundwater abstractions before contamination occurs, as that is a much more sustainable option than remediation of contamination after it's occurred, and also more sustainable than end-of-pipe treatment for water supplies, which have a large carbon footprint in both cases. So groundwater protection contributes to SDG 6, also to 3, health and well-being, and also to goals 11 and 12. Groundwater protection can be done relatively simply at many levels, provided that the community and governments are aware of the issues and take them into consideration. Techniques range from competent borehole construction with a sanitary seal, adequate wellhead protection, and appropriate distance between any pit latrines and wells. That's the local scale, up to national and regional policies to protect groundwater from surface pollution by managing waste disposal, land use, use of contaminating chemicals. And it's also part of the circular economy, because putting waste in a hole in the ground, particularly near any groundwater sources or in a shallow aquifer, is the worst option, and the waste could be used much more productively through reuse and recycling, and also help avoid contamination.
Yeah, well, thank you, Jane, very much. And this about, especially because of concentrating on waste and mentioning circular economy. I think that not only as professionals, but as human, we have to start from ourselves. And sometimes I'm really amazed how much waste I'm producing, and so we can start reducing that. And so certainly recycling. So many thanks. We will probably have one more circle of questions or some general discussion, but let me now move to our next panelist, and that's Claude Poulard. And she is a researcher and program manager at AQUIFER, and that's quite an interesting organization delivering high quality research and based in the middle of Africa, which I particularly like. Claude, are you with us?
Yeah, good morning. I'm
good
here.
Morning. Good morning. I was just thinking, you know, this session is about building healthy and resilient communities, about the future. And since you are one youngest or one of the youngest here, I don't know about the others, but this will be mostly your work. So one of the increasing threats for groundwater quality is microbial pollution, which is your field of work. So I would like to ask you to give us some insight in this pollution and associated factors.
Of course. Thank you, Neno. Yeah, so previously, geogenic contaminants like arsenic or fluoride got a lot of attention, but attention has also grown on microbial groundwater quality and more specifically on fecal contamination, because it became a big health concern, especially for diarrheal disease that cause 500,000 deaths per year, especially in sub-Saharan Africa and South Asia. And it's also the second cause of death for children under 5 at world scale. So one of the main pathways for groundwater microbial contamination is the poor structural integrity at the water source, like unsealed tube wells or cracks in the cement slab that can facilitate the intrusion of contaminants by direct infiltration from the surface. But the source types plays also an important role in groundwater microbial contamination. And for example, unprotected source or dug wells are more prone to fecal contamination than other groundwater sources like protected source, protected well, hand pump, or boreholes. There are different factors of contamination. And among these different risk factors, we find that anthropogenic activities are determinants of fecal groundwater contamination. Urban and high population density areas are more prone to fecal contamination, as poor sanitation, livestock, or domestic animals are important sources of fecal groundwater contamination. But the extreme weather can also impact the groundwater quality. Heavy rainfall, for example, increases the runoff and flush surface contaminants toward the aquifer, or can directly contaminate the tub well if the wellhead is not well protected. Flood can damage water and sanitation infrastructures, increasing the total cost of these infrastructures. And temperature can also increase the risk of microbial contamination. For example, higher temperature can favor the growth of bacteria, and drought period can concentrate microbial contamination in limited water supply. But microbial groundwater quality is also facing future threats, including urban expansion. So according to the UN projection, a population living in urban areas will increase from 55% up to 68% by 2050. And combining urbanization and population growth, we can expect 2.5 billion people living in urban areas in 2050. And 90% of this increase will happen in Asia and Africa alone, threatening the water quality. And finally, there's also the climate change, which is a big threat for groundwater quality. The Intergovernmental Panel on Climate Change, IPCC, states that there's a very high confidence that increased risk of food and waterborne diseases can be expected if climate change continues. And so indeed, climate change will increase the risk of extreme climatic events like heavy precipitation, high temperature, droughts, and floods. It's thus because important to mitigate this risk, and few things can be done. For example, developing safe and sustainable water and sanitation facilities, developing protected land areas. Some studies have shown that forest coverage improves groundwater quality and buffer the risk of flood, and new technology can also help to reduce degraded water quality. Thank you.
Many thanks, Chloe, and I'm very happy that you round off your intervention with some suggestions for the action, because it's really needed, and this is one of these pollutions which are not so obvious, but then when you come up with the data that 500,000 of deaths per year of diarrhea, that's really striking and threatening, and stressing the urban areas and increase of population in urban areas. And Jane also mentioned that how important it is really to protect water supply from waste disposal, and to seal seal these disposals properly. Many thanks, and now we will move on, and we will move to Hartwig Kramer, who is head of global environmental monitoring at UN Environment. Hartwig, are you around? Are you with us?
I'm with you, and you see me not being eaten by the crocodiles behind me, which are actually indicators of good surface water quality. But,
okay. Oh no, I was just wondering who is Hartwig. I see a couple of guys there. Oh, this one in the front. Okay.
I can be each of the three of us on the. It depends.
Very good. Very good. Good to see you, Hartwig. And well, you know. With you, we can really chat about a lot of subjects on water and environment, but groundwater, the role of groundwater and environment, as we know, is very complex. If we are thinking, for instance, contribution to the groundwater flow, to groundwater to environmental flow, but then if we add a human impact, and if we add climate change, the situation becomes even more complex, also regarding the quality. So I would just like you to elaborate a bit on this complexity of groundwater quality in relation with the environment. Please.
With pleasure. Thanks, Nino, for giving me the floor on that. And I must say it's very tricky to actually chip in as a panelist if everything has almost been said already, but not by everyone. So I try to synthesize a little bit. So yeah, the complexity lies in the detail of the scale and scope of the actors concerned with groundwater issues. I mean, aquifers can be transboundary, the drivers are mostly local, but we also need to tackle with local solutions partially global drivers, as were just elucidated by Chloe and others with regards to climate change and urbanization. In my manuscript, I was kind of, which I'm not reading out actually, I was thinking about an area such as the Mediterranean, for instance. We have already seen temperature rising by 1.54 degrees, and expectations are even more. This is an arid region. It depends on groundwater much more than any other. And it has, different from the urbanization driver, it has this fancy driver called tourism. It has been gone down due to COVID, of course. But what that actually means is that the population locally around the Mediterranean coasts, drawing on groundwater resources, relying on groundwater resources, whole sectors such as tourism, urbanization, transport, it is tripling on a seasonal basis. So it is expected to go up from annually 200 million tourists to 600 million tourists by 2050. That's basically the population doubled on a seasonal basis. There's other examples out there. So, I mean, we have to tackle a seemingly invisible and unlimited issue, because nobody sees groundwater, nobody, or very rarely is it tasting in a way that you really feel what's in there. And I'm grateful that Claudia mentioned the perspective paper, because I mean we are running the ground with the World Water Quality Alliance because UNEP is trying to shift the needle from being purely normative to move towards action at scale. And that already says it, what Cornelius figured out at scale. It's a social engagement process. Biggest challenge in my eyes and biggest solution opportunity is not purely in the data, but it is building the actors across the different SDGs, across the nexus dimensions of food systems, waste systems, urban planning, industry, tourism business, to come to the table, be convened around the available data, around the data they can bring, including from private sector, and then have them develop their own compelling narrative and test the hypothesis they need to run a sustainable business. And I guess that is probably the most critical bit. We have heard in other sessions in the World Water in the World Water Week already that the Internet of Things, digital transformation, technical cooperation is not the ultimate solution unless it is really built around a narrative that's compelling to really attract the people be around the table. So the Friends of Groundwater will need to pick that up in the assessment, which we are collectively kind of co-designing now. And that is what I would kind of conclude with. That's where science, governments, and we as intergovernmental organizations and actors have to build the bridges to connect the worldviews, which are very different. And I guess where the local situation comes to the point, arts can be an enormous narrative to underpin that message and bring those people on board who naturally don't have access to the data or are not so much concerned except to get the water on the table on the next day.
Well, many thanks, and many thanks also taking this very broad perspective, and what you address could be also conclusions of this session. Really, totally agree with you that what is crucial and this cooperation across the sectors and all kinds of players, and that's the core. That's the core of our efforts towards solution, and global drivers, local solutions, and certainly Mediterranean region. Coming from that region and seeing the changes in the last decades, it is certainly a good example of all these changes and what we need to tackle. And last, thank you for mentioning Friends of Groundwater, because all actually panelists here and presenters are part of this wonderful initiative, which is initiated within the World Water Quality Assessment led by UNEP. And it is really, to my experience, an excellent example of getting together and producing something which is of benefit of all. Thank you once more. Thank you to all panelists, and we are approaching end of this session. So I would like just in the last 2 minutes to wrap up and to close the session. I wanted at the end to address a little bit more challenges which are ahead of us, and methodological challenges like upscaling local information to a regional assessment, to remind on 4 dimensions of groundwater systems, because we have three-dimensional water reservoirs, but then we also have a time dimension, and to remind on the poor sampling and analysis, but luckily Joel and Jane addressed that. And of course, it's a data information challenge and variability of groundwater quality data across the globe, importance of the monitoring programs, which Claudia talked about, and inclusion of new advances in Earth observation and citizen science, which we all should use in modeling of contaminant fate and transport. But the most important is actually this synergy among people. So in that sense, SDG 62, I think, on ambient water quality and the World Water Quality Alliance are really crucial here. The last word is next year is Year of Groundwater. We will have World Water Forum and World Water Day, World Water Development Report, and Summit. So all of this dedicated to groundwater, and this is really unique opportunity for all of us to contribute to preservation of groundwater for new generations. You can join us in these efforts in many ways. Just contact us. Thank you.